this is really the first lecture. Huh? What I've shown you up till now is what's going to be in all the lectures, and here's the first one where we're really going to speak about the introduction, and I'm going to give a lot of definitions which are necessary for the rest. I'm going to describe the notation, describe the problems, and give a lot of definitions. And mathematics is the way we always start by defining what we're going to do, all the variables and all that we're going to need. So I like to take Albert Tarantola. He was a very intelligent guy. I knew him personally. Unfortunately, he died not long ago. And so our big challenge here is to use, why is data assimilation called data assimilation? Because we have data. What is the data? The data are observations. We saw yesterday, we can observe and we can measure, okay? We can measure things. Afterwards, we would like to use these measurements to be able to say how the system is going to evolve. We want to know what it's going to be like in 1 hour, if it's weather forecasting, or tomorrow, or in 1 month, or in 1 year, whatever. It depends on the problem. So, and all these observations and these measurements, of which we have more and more. You know, there's satellites, there's imaging, there's weather balloons, there's even medical imaging. There's a lot of data available. Genomic data is also data, right? So we can have genomic data, we can have image data, we can have data coming from the internet. There's a lot of data. These are observations. We want to use these to infer or to find the values of some parameters within the equation. Because why do we need to find the parameters? Because in order to predict, we have to find the parameters of the equation, which we don't know. If we knew the parameters of the equation, we could use the model to predict, and we would be fine. We wouldn't make any errors. But of course, we make errors because the systems have incomplete knowledge of the parameters that should go into the equation. No equation is perfect, as you said, they're models. Okay, so we have to seek, it's an inverse problem. I'll explain to you what an inverse problem is. We have to seek in some way the best solution, implied by the data. And then in fact, this has to do with the philosophy of science. We should use them just to falsify. Anyway, I'll speak about falsification, which is something else. But you know the famous saying, you find a needle in a haystack. Solving inverse problems, it's like looking for a needle in a haystack. And it's very hard, especially when the haystack has hundreds of dimensions. And in fact, in data assimilation problems, the dimensions are the dimensions of the optimization problems. We're optimizing over a space, usually Rn, and n can be very large. It can be 10 to the 6, 10 to the 9. We can have 1 million, even 1 billion unknowns. So we have 1 million degrees of freedom in our optimization problem. Oh, in reasonable optimization for data assimilations, we'll have hundreds of thousands of parameters. What are the parameters? It's the distribution of pressure or temperature over a region of space. If we're dealing with 3D, you saw my whale head. I have a 3D whale head, and the parameters that are unknown are the physiological characteristics of the different tissues in the whale's head to be able to understand how it generates sound and how it communicates. So all the points, you know that if we want to solve a differential equation or any type of equation with a computer, we have to discretize. We have to take x, we have to take the domain of space and the domain of time. Just say we have 1 dimension x in space and 1 dimension t in time. We have to divide it up into small pieces, and we make what's called a grid, and we solve the problem instead of solving the differential equation. We cannot solve for a continuous variable. We have to solve for a discrete version, and that's where numerical analysis comes in. And then these discrete points create a matrix in the end of very, very large size, order of 10 to the 6, just up to 10 to the 9, and even beyond. I've even seen problems of 10 to the 10, which we would like to solve. So of course, finding a needle in a haystack when the haystack has a dimension of 10 to the 12, you can imagine it's not easy. So don't be too despairing. Fortunately, mathematics, we saw yesterday, mathematics is very powerful, and that's why we need mathematics to be able to solve these problems. Otherwise, there's no chance whatsoever. Otherwise, we're doing like Google and trying to find 2 images that look one like the other. Okay, you can find an image that's similar to another image, but here we want to find unknown parameters of physical systems which are very complicated, and you can imagine that we cannot just use something as simple as image recognition. So the plan of the lecture, I don't know if I'll finish everything today, but because we started late, but I'll continue tomorrow. So we speak about context and challenges. I'll explain to you why it's important to do data assimilation. Then I will need to define inverse problems, of which data assimilation is a special case. Inverse problems is the general framework, and data assimilation is a special case of inverse problems. Not that special, but reasonably special. In other words, instead of just looking at data assimilation, which is a special case of inverse problems, mathematically it's more interesting to look at inverse problems, and then it's very easy, once you understand inverse problems, to solve a data assimilation problem. And inverse problems are interesting for many other reasons. I'll show you, just to show you the complexity, I will show you a comparison on a really a really quite simple problem, which we call a toy problem, but it's reasonably realistic because it has many applications, of how to perform inversion in a deterministic case, in other words, where there's no noise in the system, and how to perform inversion in a statistical case. And I'll compare the two so you'll be able to appreciate the complexity. I warned you, it's not easy, but it doesn't mean that it's, that we shouldn't solve them. Because it's not easy, it's more interesting to solve. Okay. Then I'll give if I have time today, all the notation and all the definitions necessary, the names of all the variables. In the data assimilation community, starting in the 80s and the 90s, they decided to have a very consistent notation system to describe all the variables, and you'll see there are quite a few different types. And so everybody who does data assimilation uses a standard notation system, which is very good, which means you can exchange codes, we can exchange theories. It's very easy because everybody does the same. I'll make some conclusions. So, okay. So in the context and challenges, I'll speak about, we'll speak basically about model space inversion, data space inversion. This is more advanced, but I'll give you just so let's see what is so. So what is the challenge? In fact, we have a forecasting challenge. We want to know how a disease evolves. We want to know how a population, how a virus propagates, how the weather changes, how storms arrive, how fires propagate, how the jungle is destroyed or it's going to develop. And basically we have 4 Earth systems that we would like to be interested in. We have hydrosphere, atmosphere, geosphere, and biosphere. There's a lot of challenges out there. But what characterizes these problems is they're multi-scale, they're multi-physics. There's not a single physics in a problem like this. In a problem like this, there are many physics that are combined. It's not just, I don't know, propagation of heat propagation. It's heat coupled with wind, coupled with humidity, coupled with many physics are involved. There's chemistry involved. There's physics involved. Many things. Most of the systems we're interested in are nonlinear, and nonlinear systems traditionally are much more complicated, both in theoretical terms and in practical terms to solve. Okay. And then, of course, it's stochastic. The world is not deterministic. If the world is deterministic, we would know when we were going to live, when we're going to die, if we get sick, if we get better, if the virus will propagate, if the virus will... We don't know these things. That can be modeled, but mathematicians have been thinking about this for a long time, since the days of Gauss and Euler. And so we know how to reduce, or what we call manage the uncertainty. So we call this uncertainty quantification. We can quantify. In other words, we know that we don't know, but we can quantify the extent of our lack of knowledge. This is very important because you have to admit that there are things you don't know. If you don't admit that, then you'll never know them and you're never going to take them into account. So in data assimilation, because we want to solve these problems, we have to admit and take into account the fact that we don't know things. And that's basically, that's what makes it a little more complicated than solving AX equals B. We have AX equals B plus epsilon, or zeta, or eta, and eta is stochastic. It's a noise. It's something that we don't exactly know its value. It can have values with certain probabilities. We have to take that into account. And then, of course, you'll see that all these problems are data intensive and compute intensive. There's a lot of data. That's why the matrices are very big. And they compute intensive because we want to solve problems using very, very big matrices. Why do I say matrices? Because if you've seen, you've not seen, traditionally, when we want to solve a differential equation, which is defined on x and t, x can be x, y, z. These are continuous variables. To solve them, we have to discretize. We have to chop up the intervals. or the spatial domain and the time domain into small pieces, and then we solve at what we call grid points. So we get a compute intense, we get big matrices to describe the problem, very big vectors. I told you the vectors can have a dimension of 10 to the 6 or 10 to the 9. Millions and billions. They're not little 3 by 3 systems that you want to solve. It's not even 10 by 10, but it's million by a million. These huge, huge, huge systems. And so there's a lot of problems of computation which has to be taken into account. So you see, the challenges, there's no shortage of challenges. This is for you, the challenges. I'm already, I've started and I realize that there's still, the more we advance, the more we realize that the challenges are still there. There's still plenty of challenges for you people to study. So, okay, because it's complicated, one needs to think about how to think. So I won't go into this, but if you're interested in knowing, this comes from philosophy of science. This was a philosopher of science, Charles Peirce, who lived in the 19th century in the United States. So he wrote a whole treatise, which is considered the main reference about to move from reality to decision making. Because, oh, of course, why do we want to model and predict? Because we want to take decisions. Don't forget. Don't forget. Somebody's going to decide. Are we going to, are we going to lock down, or are we going to use vaccination? Let's take COVID because everybody knows COVID. Should we use a vaccination? Should we use confinement? Should we use quarantines? All these things require decisions in many respects about whether to take preventative measures, etc. So, because these are very complicated, there's a whole what I call the inference cycle. We want to go from theory to predictions to observations, and then from the observations we want to improve the theory, and from the theory we want to get better predictions, and then the better predictions we confront the predictions with observations, and then we have what's called a cycle. In fact, we never finish the cycle. Why? Because we never have perfect knowledge. We never know exactly what's going to happen tomorrow. So knowledge seeking or solving problems is in fact a cycle that continues and continues and continues. And I don't want to disappoint you, but it never really ends, because perfect knowledge is never attained. Nobody, well, no humans that I know have perfect knowledge of what the world is going to be. So there is, fortunately, and this is in my new book, the first book I call the DA book, the one on data. The other book I call the DT book, because it's on digital twins. And in the DT book, because digital twins are complicated, one needs some kind of guidance about how to solve problems. And this is an approach. So if you're interested, anyway, we don't have time. I could spend hours just talking about this, but we weren't going to. So there are tools available. So let's start with the very basic definitions. We will need all of these things of an inverse problem. So the inverse problem basically means that we have a source, we have an array, and that source goes through a medium, but the medium is not completely known. It's an unknown or poorly known medium. The medium can be anything. It can be a human body, it can be the Earth when we're doing geological prospecting, human body when you're doing imagery to detect where we have that something's wrong. There's a tumor, there's a malformation, and we have some kind of source, some kind of signal. Usually we send a probe, we call it a probe. It goes through, propagates through the medium, and it's measured on an array, right? So in terms of mathematics, you see I have a source function S of x and t, which goes into the model. I can call it L, whatever, which depends on U is the unknown, M will be the model parameters, and it's excited or pushed by the source. And I get the solution U at XR, R for the receivers in the array. So in a parameter-dependent dynamical system, so for L I can put anything. Let's take parameter-dependent dynamical systems. Typically it's U dt, it's a very simple system, equals S of t, U, and M. M will be my parameters. Sometimes I call them theta, sometimes I call them M. And M is for model, but there are two different ways of describing this. And this system will usually have an initial condition. It's a system, let's say it's a system of ordinary differential equations. Okay? And we suppose that S is known. In other words, we can control the source. So we're going from the input to the output, from the cause to the effect. Okay. So The forward problem, which is what we spend a lot of our career in, a lot of our university and at school, is that I give you M, I give you the parameters of the system, which means, let's say, the material properties, or I know the densities of the organs in the body, or I know the speeds, the acoustic speeds of the rocks in geology, or I know the characteristics of the atmosphere if I'm doing weather prediction. And so I give you all of those, and I give you the initial condition, U0, and I say, I'll ask you to find U of t. That's the direct problem. Very easy. I mean, you know, it's cause to effect. I give you everything that's on the left, and I'll ask you to find what's on the right. Okay. But the inverse problem says that I'm going to give you the U of t. What's U of t? I'm going to give you the response. I'm going to give you the right hand. I'm going to give you this. Okay. I'm giving you the solution. Where do I get the solution from? Not because I solve the equations, because I have measurements and observations. So the measurements, the observations, they know the system. Nothing knows the system better than the measurements. The measurement contains all the information. The trouble is how to get that information. So I want to find M, which sometimes I'll say belongs to a space of the model parameters, okay? So that's the inverse problem. This problem is not easy to solve. I'll show you the difference between the two, obviously. So you understand we're trying to invert the causality. We're trying to invert the world giving us observations. And from the observation, we want to go back from the effect. We want to go back to the cause. Okay, that's what makes it more complicated. In fact, why is it complicated? Because whereas the direct problem, this problem, the UDT equals S, and you given the initial condition, we know that, you know, we have theorems that say existence and uniqueness of that system. Well, it's enough that S respects some kind of Lipschitz condition, when that can even be weakened, and U0 must be in a certain space, functional space, and the solution exists and is unique. But for the inverse problem, we don't have existence and uniqueness. We might have existence, but we definitely do not have uniqueness. That's the difficulty of the inverse problem, is that many combinations of M could give you the observations, and we need to get the good one. And this will be, these problems are what are called overdetermined or underdetermined problems, and we need to find some kind of optimal solution. It's a little bit like a regression problem. We don't have a single solution. There are many solutions possible, and so what we will look for is an optimal solution. And that's why I said that laser simulation is some kind of optimization, and even a Kalman filter, which is a statistical inversion, is also an optimization problem. It also solves an optimization problem. So we always need, for solving the inverse problem, to use some kind of optimization. DA is a special case of inverse problems where I give you measurements, as usual. I give you the right-hand side, the array, what I've measured, my observations, and I ask you to find the initial conditions. So DA is a special type of, a special case of the inverse problem where I'm looking mostly for U0 for the initial condition. And that initial condition in terms of weather forecasting, enables me to predict from where, I know from where to start for the next time interval. So I can predict forwards on a new time interval if I know a good value of U0. Okay, so that's the DA. So I'll show you that, and we'll speak about this a lot. Data assimilation, in fact, is an iterative process where you have observations. These observations will go into the model, and this model output and the instrument output will be compared. So the model will make some prediction. I'll compare the prediction of the model with my measurements, my observations, and do a simulation in order to change the model. What am I changing? I'm changing the parameters because I'm looking for M or I'm looking for U0, such that my model prediction and my instruments agree. I want the model to become as close as possible to the observations. Then I know that my model is doing a good job because it's following the reality, right? Otherwise, it's, you know, the model is giving us a solution. We don't know if that's, to check that solution, we want to compare it. We can, fortunately, compare it with observations. And then the question is, how do I adjust the model so that it compares better and better, gets closer and closer to the observations? Then I can have more confidence in my model, and then I can make decisions based on the model with some confidence. Otherwise, you can say, okay, here's the model results, but if you don't compare what the model does to reality, it's difficult to make good decisions. So for the observation, we will introduce also what's called an observation equation, because the observation, we only have the observation at certain points, so we don't know the solution We cannot measure the solution everywhere in space. Imagine 3D, imagine weather forecasting. We cannot measure the solution, the temperature and the pressure. Let's say we were looking at temperature and pressure. We cannot measure it everywhere. We can only measure at selected points. So we need some kind of equation to describe the observation. And usually we also have a discrete number of observations. So it'll be a set of observations, and these observations will always have some kind of uncertainty in them. They're different observations. There's always noise, which will have to be taken into account, and we will take it into account. I'll show you. That's basically the secret of data assimilation. The reason why we can do that weather forecasting, because everybody knows the reason why weather forecasting works reasonably well is that we take into account the uncertainty. Weather forecasting does take into account the uncertainty. Okay, so in a typical inverse problem, we come to the definition of an inverse problem. We seek to determine plausible values, reasonable values, because we're never going to know the reality, the truth, right? We don't have any pretension. We're not pretentious to say, we're going to find the true values. Of what? Of the model parameters. And what are we given? We're given inexact or uncertain data. Data is always inexact or uncertain. We can never be sure, because mostly, first of all, instruments have uncertainty. Instruments are not precise. And then the fact that we cannot measure everywhere means we have a lot of uncertainty in our measurements because we don't have the measurement everywhere. And we have an assumed theoretical model which relates the observed data to the model. Okay, so we need these. So, and we seek, using this model, to determine plausible values of the model parameters. So the model parameters can be either the description of the medium, or it can be, as in the case of the data assimilation, the initial condition. So these are difficult problems. They found in almost all areas of science. That's why it's a very powerful method. In engineering, in medicine, I just take from geophysics. It's used for forecasting performance of geothermal reservoirs, for extracting oil and gas, for estimating pathways of subsurface contaminants, transport, this is ground pollution, for hydrology, for groundwater management. I just took geophysics. Now, I can make you a list of many pages of the potential problems where we would like to solve inverse problems. So there are many, 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 many problems, as I said. In medicine, a lot of medical imaging is an inverse problem, right? Because in fact, when they do an X-ray, or when you do echo sounding of imaging of any CAT or other types of imaging, in fact, what we're measuring on the array, and we want to use those measurements to deduce the unknown material parameters, which is, in terms of medicine, it's the properties of the physiological properties of the organs that have been transferred, that are there. Okay, so we work in these cases we create an image, but that's just a representation of the solution. Okay, so as you see, it's in many domains. The main problem of inverse problems, and this is where the mathematics helps us to understand where the difficulty is and how to avoid or how to take into account these difficulties, what is known as well-posedness. Well-posedness is a very essential notion in mathematics, which here I give it in a very broad context in terms of normed spaces, but okay, it's just to show that it has a very, very big, very solid mathematical foundation. And the problem of finding x given y. Okay, you understand? I'm giving you the measurements y, and I want to find x. Okay, that's why the problem is difficult. We'll call this problem well posed if three conditions are satisfied. These are conditions called existence, uniqueness, and continuous dependence. Okay, sometimes it's called stability. So these three properties are essential for well-posedness of an inverse problem. If any one of the three is not satisfied, the inverse problem will not be well-posed, which means that, in fact, I'm going to have a lot of trouble to solve the problem. In terms of, if I had a matrix, the non-existence expresses itself by the fact that the matrix is singular. We cannot invert the matrix. The matrix is not invertible. That's an example of lack of existence. If I have an overdetermined system, I have more equations than unknown, then I have non-uniqueness in solving a linear system. That's another example of ill-posed. When we say it's, when the problem is not well posed, we say it's ill-posed. Okay. Yesterday, Yusuf spoke about identifiability. Existence uniqueness, together we call it identifiability, and continuous dependence is related to the stability of the inverse problem. So all these things have to be satisfied in order for the for any problem to be well posed. The problem is that all, I put into brackets, interesting inverse problems are not well posed. They're all ill posed, all of them. So, okay, so we start off very badly, but don't worry. A lot of very, very intelligent researchers have been thinking about this for a long time, and there are ways to solve this problem, fortunately, and to keep us busy for the next couple of lectures. Okay. I don't have time to show examples, but in the 3 chapters that are available of my deep book, there are a lot of simple examples which show you how can show you examples of non-existence, non-uniqueness, and non-continuous dependence. So have a look at in those 3 chapters. There are many examples, I think, in chapter 1, with some very simple examples. You see that even in very, very simple cases, the problems, inverse problems, are severely ill-posed, and that's what makes them difficult to solve. Okay, so this is to know, let's understand why it's difficult. Okay, afterwards how to solve it. Okay, so since inverse problems are ill-posed, we can think of a linear system with more unknowns than equations. We have to solve for it in some average or optimal sense. The only thing we can do is some kind of average solution, some we call the best solution possible. Okay, so for this, what we usually do, and this is what we will do, we will define what we call a cost function, or a loss function, or an error function. What will be the loss or the error? The error will be the difference between the model prediction and the measurements, the observations. So I can define a positive valued cost function, and because it's positive valued and I want my model predictions to be as close as possible to the observations, if I minimize the cost function, I will get an optimal solution. Of course, I don't have an exact minimum. Any minimization is approximate because we stop after a certain point. And so that's why it gives me the best, or the average, or the best possible, or some optimal solution. So that's what I mean, mathematics comes to the rescue. The problems are ill-posed, but we can look, if we do it correctly, for the best possible solution. And that's what we can't do better than that. And then I said, of course, you cycle, huh? So don't worry. We don't think that we found one solution, okay, we can go home and sleep quietly, knowing that there won't be a typhoon tomorrow. But we know that we're going to continue looking for better solutions. And then what we would do, once we have a positive function, we can compute its gradient. So we know that if we compute the gradient of a positive function, it's going to point us, it's going to show us the way down to the minimum, right? We know that a parabola, a quadratic function, we always know that has, and these cost functions will always be at least quadratic, not necessarily, but positive definitely. And we use the gradient in an optimization algorithm. We know that, I hope you know that. If you don't know, you should have a look. Optimization algorithms, we want to find the minimum or the best solution. The most efficient way of doing that is to use some kind of gradient-based optimization problem, a problem that uses the gradient, that says we have to go downhill. If we want to find the valley, which is the minimum point of a parabola, we need to go down, down. Down is the gradient, down. The direction down is given by the gradient of the function at any point until we find a minimum. Okay. What makes life a bit more complicated in data assimilation is we're not minimizing a function, but we're minimizing a function of functions, which is called a functional. So we need to do functional minimization, and this is done by calculus of variations. Calculus of variation dates from a long, long time ago. Okay, it's Euler, and even before Newton started to express. So we have very, very good mathematical approaches for solving this type of functional minimization problem, and in particular, what is used in variational data assimilation, what's called an adjoint method. And I'll explain to you adjoint method because we will see that, strangely enough, machine learning and deep learning uses an adjoint method, which is strange. They didn't, you know, the guys and the girls who developed machine learning and deep learning, they were very, very good. In fact, some of the best students in mathematics go to do deep learning because you earn much better, right, than doing mathematics. You can go work for Google or Facebook or whatever. And they discovered that, in fact, calculus of variation adjoint method is the best way of computing a gradient. we can obtain the gradient of a function, a functional gradient. In other words, we're looking for a function and not for a value. I'll explain that soon. It's best done by adjoint method. I'll explain about that, okay? And if we're in a purely statistical setting, a stochastic setting, then we can use what's called Bayesian inversion. I'll insist a bit on Bayes formula and Bayes theorem, because Bayes theorem or Bayes law, which comes from Bayes, also the 16th or 17th century, actually provides us a solution of an inverse problem. Strangely enough, when you realize that if I use Bayesian theory, I can in fact solve the inverse problem as well. Okay, so there's some very nice mathematics, but the mathematics comes from all over the place. Huh? It's from calculus, it's from statistics, it's from optimization theory, it's from functional analysis because we're dealing with functions, and so that's why I like inverse problems, because you really see why it's interesting and important to learn a lot of mathematics, and you can use a lot of different mathematics is used to solve inverse problems. Okay, so in the end, and I'll come back to this many times, we're going to set up some kind of flow chart, some data flow for inverse problems. If you understand this, then you understand where you are. Okay, so basically we have some control variables. They go into a model. The model creates an output, y. Then I take my observations, whatever observations I have, and I compare y with d, okay? Obviously what I'd like to do is that my model is as close as possible, y is as close as possible to d. So how do I find something that's close? I'll take the difference, and then I'll use an adjoint method, we'll explain, which will give me the gradient of the cost function. So I'll be able to take its gradient, and once I know its gradient, I can use an optimization of, the cost function is here downstairs, okay? Once I know the gradient of the cost function, dj, then I can minimize it, and the minimum will give me, a minimal point will give me new values for x, which I'll put back into my system. I'll compare again until I'm satisfied, okay? So it's always an iterative process. We don't do it once, but we have to iterate, we have to turn around until we've had enough. In other words, we don't have enough. The computer shuts down, or we've used all our computer budget, or we satisfy some kind of criterion which says I'm happy if the difference between my observation and my data is of the order of epsilon, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. Different problems, we use different tolerances, and these are what are called stopping criteria for optimization algorithms. So all of this will be done in a flowchart, and this flowchart is a very different. It reminds you a little bit of what I said to you before of the inference cycle. It can be related to the inference cycle as well. You know, we never have perfect knowledge, and we try to improve our knowledge by going around and around. And here we use variational calculus, optimization, if you like, minimalization, to find the values. Okay, so I don't know for time, do I need to stop at 10? Yeah, I think I stop at 10:30 and I'll continue tomorrow, so otherwise everybody's going to be late. The organizers. I stop now. I can continue until tonight, but I'm going to stop now. No, I don't know. Are you deciding? Are you the organizer? No, really. Would you prefer that I stop now so the rest of the day is on schedule, or can I continue a little bit more?
I believe it's better to continue.
Ah, better. Okay.
Yeah.
For me also it's better. But until what time?
Until 11.
Until 11. Okay, let's go.
All right.
I got plenty. Where am I? I've got plenty to say. Okay, so thank you very much. So I'll continue a little bit, another 30 minutes or so. So just to recap, I'll give you a finite dimensional example so you have an idea. Let me just move the cursor. It's bothering me. So you have an idea of what's happening, okay? I put it into finite dimensional context, even though usually the analysis we do in functional space, not in finite dimensions, but when we look at it in finite dimensions, we have a better idea. Oh, it's not my cursor, it's your cursor, okay. You don't want to move it away. In mathematics, the cursor, if it hides one of the variables, it changes the mathematics completely. You see the cursor there, control. Okay, that's all right. That's not serious. Okay. Okay, so we have a data vector which has some dimension, and we have the model parameters, which is another dimension. Dimension usually n, and here we have p. Often we use p for the dimension of the parameter space, and we have an equation that relates m to d. What's the equation? Is g of m equals d. So if I give you the model parameters and you know g, then you can calculate d. You can calculate the data from the model and the model parameters, okay? You remember, recall, it's important to fix it in your heads. Forward problem, I give you d, I give you m, sorry, and I want you to find a d, okay? So you just apply g to m. If it's a matrix, you say, I multiply g by m, and I can find d. That's easy, you see. Everything you've been learning until now, for me, that's too easy. We know how to do it, okay? So we solve an ODE, a PDE, an integral equation, a linear system, and that's the forward problem. The inverse problem says, I give you D, and I ask you to find M, okay? So we have to invert G. If G was an invertible operator, just say it's a positive definite matrix, then it's very easy. You say, okay, M equals G inverse multiplied by D. But unfortunately, I told you, inverse problems are not well posed. In other words, we cannot invert. If we could invert, okay, we just use linear inversion theory or inversion theory and everything will be easy, but it's not easy. But, as I say, due to the ill-posedness, because why? Because n, my data, is much smaller in dimension than p. The parameter space has a very high dimension. Why? Because the parameter space, the values of my parameters, is defined at every point in space, every point in my grid. So p is 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 9 in big problems, but it's big. And n, the number of data points, the measurements is much, much smaller. I cannot afford to measure everything everywhere. If I measured everything everywhere, I would have almost perfect knowledge. Then, in terms of, you know, if n is equal to p in a linear system, then at least I have a chance of finding an inverse. That the inverse of the matrix exists. Otherwise, there's no chance for a non-square matrix, for a rectangular matrix. The inverse does not exist of a rectangular matrix. The inverse exists only for square matrices. Oh, you could say, oh, but I could multiply the square matrix by a rectangular matrix by its adjoint, and then I could get a square matrix. But it turns out that when you multiply two matrices, you increase the instability because it's a matter of conditional matrices. We won't go into that now, but there's no simple solution to this problem, to the ill-posedness. Okay. So because of this ill-posedness, I said to you, we have to minimize, we have to find the best solution possible. So we minimize a cost function. Usually, and that's why minimizing is not easy, we have to regularize. You see, my cost function is gm minus d, some kind of norm over x, some L2 norm, anyway, some Euclidean norm. If we're in finite dimensional space, this is Euclidean norm. But you see, I've added another term. This term turns out to be indispensable. It's called a regularization term, and that's what makes inverse problems more complicated, because this term of regularization is another way of fighting against the ill-posedness. So I won't go into that, but I'll give you some references. Okay, so just to say that the minimization problem is not as simple as it seems for various reasons, because of the ill-posedness. So if let me take a very simple problem, which is called a boundary value problem, which is an ordinary differential equation, which is quite commonly found. And if I discretize this, I won't go into this in numerical analysis, by finite differences, I told you we cannot solve. If we knew the solution, if I could solve this problem analytically and find a function u of x, I wouldn't have to bother. But unfortunately, you know, that the number of equations or the type of equations that we can solve analytically is a set of extremely very small measure. There are very, very few equations, in fact, that we can solve. So most equations we have to discretize and then solve them numerically. So we have simple discretization. Maybe you've seen this, I hope you've seen this. These are just approximations. If you know that we take the limit when h goes to 0 of u I plus 1, which means the u at x plus h minus u of x, divided by h, limit as h goes to 0. We know that tends to the derivative, and that's the approximation of u primed. Because you see, each finite difference is an approximation of a derivative in the limit when h goes to 0, but we don't let h go to 0. If h went to 0, it means we're in the continuous case, so we stay in the discrete where h is some grid. So we can approximate the equation by this. And then it can be written as a linear system, in fact. So all of this equation then becomes a linear system which needs to be solved. So I can solve this system by inverting the matrix, and I can find the solution U, in principle. It's exactly equivalent to what we've all learned in seen AU equals F, and I want to find U. The problem, as I said, is that for given parameters, we can solve this linear system, but note that now it's going to be nonlinear, because if we can calculate the inverse, you know that the formula for the inverse of a matrix, what was a linear problem in the direct problem, in the inverse problem becomes nonlinear, because if I can calculate the inverse of this matrix, it's going to be a nonlinear function of A, and not a linear function. So immediately I get a nonlinear problem, right? Okay. So for given observations, I'm going to choose alpha and solve this minimization problems. And usually this is done by a quasi-Newton method, or what is mostly used in data assimilation and in other inverse problems is to use what we call the adjoint method, because the adjoint method has the advantage of giving us the gradient, or an expression for the gradient of the cost function. If I know the gradient, I don't know if you've seen in numerical analysis, basic numerical analysis, if one knows the gradient of the function that we want to minimize, then one can minimize much more easily. Otherwise, we have to guess and try small differences in the problem. The problem is if a function varies very rapidly, the gradient varies a lot, and so the gradient is if we know the gradient, we can minimize much more easily, much more directly, and much more quickly. And if we don't know the gradient, we have to use very, very simple methods that don't take advantage of gradient information. And because these problems are very large, we need to have the gradient. And that gradient, I'll explain to you, we will calculate it with an adjoint method, but we'll see that tomorrow. Okay. So you see, a major part of scientific discovery and research deals with questions of the nature: what can be said about the value of an unknown or a badly known variable M or parameter represents the parameter system if we have some measured data and a model of the underlying mechanism that generates the data. So this is really a basic problem. Inversion turns out to be a very, very basic problem in science. Okay, and then the current grand challenge in CSE, we call it computational science and engineering, and of course in environmental science, is the solution of what are usually very large-scale statistically inverse problems that are governed by usually partial differential equations, and that involve large amounts of observational data. And so this is really the challenge that is in front of us, and that's what we want to do. We call this model space inversion. Okay. Another approach which is very important, which we'll be basing the statistical inversion will be based on this, on Bayes' theorem, is Bayesian inversion. So, okay. Bayes' theorem is quite amazing, because Bayes' theorem, this is Bayes' theorem, it says that it has to do with conditional probabilities. So, now it doesn't give us the solution, but it gives us a distribution of probability of a solution. So we're looking for the model parameters M, okay? And D is the data. So the direct problem, if you like, can give us the probability of D knowing M. If I know the model parameters, I can calculate D, and in other words, I can calculate by some Monte Carlo or other method, I can calculate this probability. This is the direct problem. This term is what we call the prior probability, which contains some previous knowledge of what I know about M. And I'll show you that, in fact, we often know some statistical information about prior knowledge about the distribution of our model parameters. And then the denominator is just a normalization, because you know that in the left-hand side, if I have a probability is a function that has to be strictly between 0 and 1. And in order to be strictly between 0 and 1, I have to normalize. So Bayes' theorem gives us the solution of an inverse problem. Why? Because it says if I give you D, Bayes' theorem finds M. But that's exactly what I'm looking for. I'm looking for, given the data, can I find the model parameter? So you see, Bayes' theorem actually is an inversion. It's an inversion theorem. And it's used in inverse theory because it does exactly what we need to do. It gives a solution of an inverse problem. Okay. So what are these terms? As I said, the physical model is represented by a conditional probability. That's P of D given M. It's also known as the likelihood function. That's PDM. So this is something we know from the physical model. This term, the likelihood, which is this term here, don't worry about the denominator. It's just normalization, and usually we use a trick to normalize. You don't have to know P of D. We never really calculate P of D. Okay, so the direct model or the physical model that we know, or we don't know it exactly, but we have an idea, gives us the first term. Prior knowledge or historical knowledge of the system is described by P of M. I'll show you, for example, in geophysics, there's a lot of P of M. I'll show you how P of M is known. It's known usually from experience. And if it's not known, one can also make some very simple assumptions of what it could be with. And the denominator is just a normalizing factor and not really important. Okay. From these, we calculate P of M given D, and we call that the posterior probability. But this posterior probability, we see it's exactly the inverse problem. It's the solution of the inverse problem. It's giving us the probability of the model parameters, knowing the data. So Bayes' theorem is incredible. Okay, so why don't we just use Bayes' theorem? Well, because it's difficult. It's very, very difficult computationally. It's a very complex problem, but I'll speak to that in the next slide. So from that, we can calculate what's called a map estimator. I won't go into these, but in fact, often we take a maximum problem of PMD, which gives us the most likely solution that's equivalent to the best solution in a deterministic sense. Okay, this is not very important, but it can be related to least squares and maximum likelihood. There are relations that we don't have time to go into. But the main problem of this base of a maximum type of maximum likelihood or maximum a posteriori or map estimate is that it's not enough to know one point. We usually want to know more. It's insufficient to have a point, what's called a point estimator. We want to have an estimate over an interval. And this becomes the major problem with using Bayes' theorem is that we have to explore what are high-dimensional posterior probability distributions. So that solution PM over D, in fact, it's a probability distribution, but it's a probability distribution over a very, very high dimension. Why? Because M can be 10 to the 6, 10 to the 9. Imagine a probability of function of probability, a probability function that depends not on one variable or two variables. You've seen a Gaussian that depends on one variable, X. You've seen a two-dimensional Gaussian, maybe it's like a hat. It's like a Mexican hat. Imagine we have a million-dimensional Gaussian, and you have to have, because we don't know its form exactly, we need to have a discretized form. It's very, very, very difficult. In fact, it's an intractable problem. It's not an intractable problem. This is notoriously intractable for real problems of interest. For academic problems on one dimension, we can always find this PM given D, but in real problems, it turns out to be extremely problematic. Okay, but don't worry. Solutions exist. I don't say the solutions are easy. And we can use Monte Carlo methods. We can use what are called MCMC methods, Monte Carlo Markov chain. And we can use Ensemble Kalman filters. If you want to know about Monte Carlo MCMC, it's best to look at, I have made in my new book, DT book, I've made a very careful explanation of these things. And the problem is these are very expensive. If we want to do higher resolution models and we want to have reliable quantification uncertainty, these problems turn out to be very difficult. But don't worry, I say a huge number of remedies exist. Okay, 4 or 5 years ago, a 2,053-page book was written just on the subject of how to calculate and explore high-dimensional probability distribution. Just to show you that the research community is very, very, very interested by this problem. It's a very, very challenging problem. And there's if you're interested, it's a book in 3 volumes. They couldn't put it 2,053 pages. You cannot put it into 1 volume. So there's 3. I have them on my shelf. 3 very, very thick books, over 2,000 pages, which was written 5 years ago, and I think soon it will be renewed. So just to show that, okay, a lot of solutions exist. So even though the problem is very difficult, this problem of calculating the sky, the problem is to calculate this. In fact, even though Bayes' formula gives us something, Bayes' formula is, it's okay. If you know, if you have an expression, you have a formula for P of D, M, and P of M, but we don't have formulas. We only have solutions of an equation now, or we have to have an ensemble of solutions. And so exploring, or in other words, describing PM of D is a huge problem, but some of the best researchers in the world, and a lot of them are very, very busy. The proof is that, they just 5 years ago wrote a 2,000-page book. Okay, so So there is some, I don't say it's easy, but it becomes possible. Okay, so the question is, how can we use data? Now this is the introduction to machine learning to somehow make our life a bit easy. Is machine learning a solution? Okay, so we can call it, what I was doing now was model space inversion or parameter space inversion. What about working in what's called the data space, based on machine learning? Potentially, it can obviate, which means it can completely eliminate the need for a model-based approach, which we've been doing until now. We've been using our models, right? So I say, now wait, Google says, you just look at the data, and everything is in the data. So if everything's in the data, you can solve any type of problem just by looking at the data. Why go to the trouble of using models? But, okay. This is valid, this is possible if the examples or the data are representative enough of the underlying information theoretic composition. Now, they have to capture all the information in the system, and the learning algorithm has to be quick enough to capture all the subtlety. And the problem is, you see this, in the United States, they say, in God we trust. Yeah, in data we trust. If you want to believe blindly in the data, maybe it would work. But in general, we do not have enough data. Okay, Google, when they do image recognition or speech recognition, they have access to thousands and thousands they have petabytes of information, a lot of information. When we're going to solve our inverse problems, we don't have enough data, that's for sure, okay? Machine learning, the problem with machine learning is that it doesn't take into account the uncertainties. There's no uncertainty quantification, so we get a single answer. Machine learning gives you a single answer, which is not necessarily a good one. And we need to have some idea of the uncertainty. Coupling machine learning and classical methods might be an option, and that I'll speak about in lecture 4, and there's a lot written about it in my new book. Okay, but just to say that data space inversion by itself will definitely not solve adequately the complicated environmental problems that I showed you in one of the early slides. So there's no way, don't have any illusion that you can solve these complicated inverse problems using data exclusively. We're going to have to somehow use the knowledge available from our models because the data we have is not sufficient. We don't have enough data to have what we call uncertainty quantification to quantify the uncertainties. And these only the models can do. So somehow we're going to look for. I just want to show you, I spoke about the fact that we need prior information. Have a look. In geology, there's a lot of stuff known about different lithology, which has to do with the structure of the rocks, permeability, boundary conditions, river flows, drains, aquifer recharges. All these types of uncertainty, we have some kind of information. We know that, for example, that permeability is often a log normal probability function. Pressure boundary conditions, for example, can be described by uniform probability distributions, etc., etc. So you see there's a lot of previous knowledge, historical knowledge, experience, which just comes from geophysics wells, from well data, from experience, from previous studies, etc., etc. And these are applicable in a lot of sciences. So the fact of using Bayes' theorem, people often say as a critic of Bayes' theorem that, but you don't know P of M, you don't know the prior probabilities. But in fact, prior probabilities are known, or if not, they can be estimated from historical data. So there is a possibility of using. And then I said, you remember in the numerator of Bayes' theorem, we have the likelihood multiplied by the prior, which gives us the posterior, which solves the inverse problem. The prior experience can tell us exactly what type of probability law we can use for the prior. The likelihood, that's our model. It's just our model because the probability of D given M. So if I give you the model parameters, can you calculate the data? Yes, you can if you have the model. So the likelihood is and the product of the two normalized will give me the posterior. So I can use Bayes' theorem, except that, as I said, computationally it's a problem. But as I said, 2,000 pages, etc. There's a lot of research and a lot of information is available for helping to solve this problem. Okay, so just to end, I'll show you quickly the difference in complexity between a classical inversion, not using Bayes, and a Bayesian inversion. So I took an example everybody knows. I want to where's my equation? Here it is. Here's my equation. This equation is, this is the Laplacian equation, okay? But I use here the possibility that I have a medium which has a probability, which has a property that depends on space. So instead of having Laplacian of u equals f, I have to do minus gradient multiple dot exponential of m. Why I put exponential? That's to make, just to ensure that m stays positive, because I don't want to have a changing sign. An exponential will always be a positive function times the gradient. If m was constant, I could take it out of the parentheses here, and then I would just have exponential of m multiplied by minus gradient of minus Laplacian of u. So it's just Laplace's equation. It's a Laplacian equation, and I have some kind of conditions. And this can be completely described, and this is a very classic problem because it's a prototype problem for many other PDEs, contexts, and problems. The Laplacian operator, this operator here, is found in reaction diffusion, in population dynamics for the spreading of, for the spatial spreading. In chemistry, it's found to some extent in meteorology, but you know, meteorology is nonlinear equations. There's a very famous operator which is found everywhere. So I can solve a direct problem. If I give you f and I give you m, I want to find u. I have to solve what's called Laplace's problem or Poisson's problem. And I can also pose an inverse problem saying that I give you u and I want to find m. That'll be the inverse problem. And I'm going to do that numerically. Okay, so I will solve first what's called the direct inverse problem. The deterministic inverse problem, and then I'll solve a probabilistic inverse problem. Just I want to show you, I won't go into the details, but I'll give you some reference at the end. And one can solve the deterministic inverse problem many times, and in such a way create an ensemble of solutions and somehow approach the Bayesian inverse problem. Because what is really interesting for us is to be able to solve the Bayesian inverse problem. Why? Because the Bayesian inverse problem doesn't give us one solution. It doesn't say that m equals 5. It says that m, which is much more intelligent, is m is a certain distribution of probability, which means it's most likely to have the value 5, but with a probability of 0.2 or 0.3, it can vary between 3 and 7, okay, which is much more interesting because in fact, the temperature tomorrow will never be, well, okay, here it's quite constant. This is not a good example, but whatever. The prediction, the temperature prediction, or the precipitation, let's say. Precipitation is very difficult to predict. Temperature is pretty easy to predict. Okay. Precipitation, we say tomorrow there's going to be 10 millimeters of rain, but in fact, 10 millimeters is the average or the most likely value. What's more interesting to know if you want to take prevention against flood or evacuate or do kind of things, to know that there's a certain probability, with a certain probability, the rainfall tomorrow will be between 5 and 15. If it's 15, maybe we have to take precautions. So the probability, you see, gives you much more powerful decision-making tools than to have a single solution. Because a single solution, there will never be 10 millimeters exactly tomorrow, even if I predict it. It'll be 9.5, it'll be 11, it can be 15, it could be even 100, that's with a small probability. And if I know the probability, of course, I have a much better solution, a much richer solution, more information, okay? That's why probabilistic inversion and Bayesian inversion is what we seek, what we strive to reach, even though it's more difficult than the rest, okay? So anyway, I just want to show you the difference in computational complexity. So I solved this problem, the Laplacian problem. So I did what are called deterministic inversions to see how much the cost evolves as a function of problem size. So I give myself the solution and I try to find m. So I just show you here. This is for solving the Poisson problem, the direct problem. Let's look at 256. You see, to solve a problem of 256 by 256, in other words, 2 times 10 to the 4, 4 times 10 to the 4. 50,000 unknowns, a system of 50,000. My matrix is 256 by 256, okay? It takes 0.6 of a second on my laptop, okay? Solving the direct problem, not the inverse problem. The same problem, 256, solve the inverse problem finding m given u, 300 seconds. Divide 300 by 0.6. You're approximately a factor of 500, huh? Okay, so it's 500 times more expensive to solve the inverse problem than to solve the direct problems. This is just solving Laplacian u, or k for m times Laplacian u equals f. And this is solving find m given the solution u. Okay, so you see already there's a factor of 500. Okay, this is just for the determining. So you see here's 500x. Yeah, I wrote it here. 500 times more expensive because it's complicated. I have to calculate the gradient, I have to iterate, etc., etc. Okay. You look at the 512. You see here you've got 3.6, and here's already 3,000 seconds. And the 1,024 I didn't even try. It'll never finish. I would say my computer would still be computing if I had to. You multiply that by a factor of 4. It takes too long. Then I can draw. As n increases, I can draw the CPU time for the direct problem, for the inverse problem. Afterwards, I'll put them all on one graphic so you can see, you can compare. Okay. So what you see is that the computational cost for a direct solution, it goes like, it scales of the order of n squared, which n is the size of the problem. But the computation of the inverse problem is approximately n cubed. So there's one order of complexity, which means more expensive to solve the inverse problem. So for the Bayesian inversion problem, I'm going to be given the observation. I'm given the observation and some forward model, and I want to find the posterior probability distribution of the parameters conditioned on the observational data. That's my P of D given M. Okay, so I can solve this by using Bayes' theorem. We saw that before. I just want to show you the solution. So anyway, I won't go into this, but there is a very nice theory which can be applied to what's called Darcy's law. Darcy's law is a very, very nice law because it describes a lot of physics, all the way from geophysics to batteries. Lithium-ion batteries today for electric vehicles, we modeled using Darcy's law already. So this Darcy's law is a very, very good law which enables us to find a lot of, and the inverse problem is to find the permeability K from observations of the pressure. There's a pressure equation in the interior of the domain. So anyway, there's a very nice paper, I give it the reference at the end, by Andy Stewart, who's a very, very good probability person, who gave a very nice theoretical framework for this. I won't go into it, but there is an existence theorem, which he's the first one to have shown this, which gives the existence of this inverse probability distribution problem, this posterior probability. I won't go into the inverse, but what I wanted to show you was, I did the simulations again. So here you see, whereas before I was around 300 seconds, I'm almost at 2,000 seconds for a 256 by 256 problem, n equals 256 for the Bayesian inverse problem, because I'm trying to, it's using a stochastic Monte Carlo method with something. It's quite common. I just wanted to show you, if I put the CPU times one on top of the other, way down here, this is my direct problem. This was the deterministic inverse problem, and this is the Bayesian inverse problem. So if you look down here, the cost of the Bayesian inverse problem is between 2,000 and 25,000 times more expensive than the direct problem. So up till now, if you want to solve direct problems, you want to solve the Laplacian u equals f. It's nothing. It's 0.5 or 0.6 seconds on a computer. But solving the Bayesian inverse problem is up to 25,000 times more. So what I can solve in 1 second in a direct problem, I might need 25,000 seconds. In other words, 10 hours, approximately 8 hours, 7 or 8 hours to solve a problem that otherwise in a direct problem is 1 second. So you understand that why I said it's a big challenge, because this is one of the major challenges, that we have to be very careful in the methods we use because of this computational, what's called computational. I said to you, the problems, not only are they complicated, but they also compute and data intensive, and this is the, okay, so I'll stop here, and tomorrow, before starting the next lecture, I will just give all, this is basically just what I have to do. I just want to go to the references, is to show all that I've done here is is I put the definitions of the different, all of this will be covered tomorrow. I just want to go to the end so I can show you this is all the notation, the definitions needed for, as you see, to solve data assimilation problems, we need, sorry to go quickly, but I just want to get to the end. I will show you all of this tomorrow. And these are the two, so the two major references, my book, which is, it's a very good book because it's very accessible and very easy, and I give a lot of simple examples, but as I said, there's the book of Law and Stewart, the same Stewart who wrote the existence theorem for Bayesian inverse problems, which is a very, very, you see that the paper is over 100 pages. It's 108 page paper, but it's a very, very good paper, and I recommend anybody who's interested in understanding theoretically why the Bayesian inverse problem is viable, is doable, should look at Stewart's paper. And Stewart wrote also a book on mathematical approach to data assimilation, which I think is also very, very good. So, okay, with all of that, I thank you very much. Tomorrow we'll continue.